Hello, welcome to the first tutorial video and lesson on differentiation. Okay, so if this is your first time of watching a video on my channel, kindly subscribe to the channel for more videos. Okay, so let's start. So in this video we'll talk about the basic definition of differentiation and how to differentiate polynomial functions. Okay, alright, so let's say I have the curve of a certain function, let's say f of x. Okay, these are f of x, that is the line. Then if I choose some arbitrary point on the x-axis and y-axis, okay, let's say I choose x2, I choose something like x1, and then let me put the x2 somewhere that we can get a clear picture of what I'm going to explain. Okay, so let's say these are x2. Okay, so it comes and cuts it like that. This is how this one also cuts. So if I move straight to the y-axis, I'll get my y2 here, and here I'll get my y1 here. Okay, so if you want to know the gradient of this function or the gradient of this line, then we are saying that picking any 2 points on the line is the same as y2 minus y1 over x2 minus x1. Okay, but you could see that y2, okay, y is this is the same as y. Okay, f of x can be written as y, so it's like f of some y2 minus f of y1. Okay, or let's say let me put it this way. Okay, the y is the same as f of x. Okay, so it's like f of x2 rather. Okay, so this is like f of x2 minus f of x1. Okay, all over x2 minus x1. Okay, so let's see, what if we want to call these are x2 and f of x2 by something. Okay, so if you let x2 minus x1 be equal to, let's say, change in x or delta x, and from the graph you could see that if I'm moving from x1 to x2, then x2 is approximately equal to this is 0, right? So after moving from 0 to x1, if I want to get to x2, I have to add the difference between x1 and x2. Okay, I have to add the distance here to x1 before I can get to this x2. Okay, so x2 is actually equal to x1 plus some delta x. Okay, if that is the case, then f of x2 will actually be equal to f of x1 plus delta x. Okay, I hope this is okay. Alright, then from the gradient function we say that our gradients, okay, I'm cleaning the down part, so I hope you remember. I'm saying that our gradient is equal to f of x2 minus f of x1 all over x2 minus x1, that is what delta s, so I can put it like this, and this is the same as what f of x1 plus delta x, okay, minus f of x1, alright, over delta x. Okay, that is the gradient. Okay, so the gradients of this function can be rewritten in terms of x as this. Okay, now I'm coming to I'm coming to erase the graph, and we'll go through some steps to actually write a final and the basic definition of differentiation. Okay, at any point s, okay, at any point s, my gradient is given as f of that x plus the change that you move minus f of that x that we don't know, okay, all over the change. Okay, so now what if the distance between on the graph, okay, on the graph we're having some x1 x2, okay, what if the distance between this x1 and x2 keeps on decreasing to the point that we get to a point that we move from x1 here, let's say we have our x1 here, and we move very short distance before we can get our x2, so that our distance is getting closer to 0. Okay, that means the change in x is approaching 0. Okay, if that happens, then it means that we can't do anything about it but then to consult or call some function that we know in mathematics, and we are trying to say that the distance between x1 and x2, that is this, the distance between them, right, it's actually a distance. So the distance, that's why I've brought absolute. It means that no matter how they are, the distance will still be the magnitude. It's approaching 0. Critically, it is approaching 0. Okay, now we can't just do this in mathematics. You can't just put 0 there. We have to call some function that we call the limit. Okay, if that is the case, let's see if I have the graph somewhere here. Okay, this is my y and this is my function. Okay, so we are considering a situation whereby the distance from x1 to x2 is very small. Okay, it's pretty small to the extent that it gets in towards 0, and the distance between y1 and y2 is also very small. Okay, so this side and this side, such that it is very small, and you call it dy. Okay, that's a very small change in y, and you call the distance between x1 and x2 to be what? Dx. Now the gradient, the smaller gradient that we can get is what? The change in y, which is our dy, over change in x, which is our ds, and we said it's equal to what? A situation whereby the distance between x1 and x2 is approaching 0, and that we use a special function called the limit, as our delta x is approaching 0 of our f of x plus our delta x. We will define this from our previous graph that we drew, okay, minus our f of x all over change in x. Okay, and this is what we called differentiating from the first principle. Okay, so this is how we got this idea. It's not anything difficult, you already know it, just that mathematicians were thinking about the change to be very, very small to the extent that the change will be turning to 0. Sometimes some books uses delta x to be a certain height. Okay, you can also say that. Okay, so in place of delta x, you just place h. Okay, it's depending on how you were taught or your belief, you can replace it by anyhow. Okay, all right, so let's start with differentiating some functions from the first principle. Okay, so we've been able to prove that our gradient function, which is the dy dx, is now given by what? The limits as our delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Okay, so now with this, let's see if I have a certain function f of x equals, let's say, x. Now the dy dx is given by limit as delta s approaches 0 of f of x plus delta x. Means that wherever I see x in this, I put x plus delta s there, then minus f of x, which is x. Okay, all over delta x, and this is equal to limits as delta x approaches 0 of delta x over delta x, and delta x over delta x is 1, so we get limits as delta x approaches 0 of 1. And according to the rule of limits, the limit of a constant is the same constant, so here we get 1. This means that whenever you have a function that is x just of 1 degree x like that, the derivative or the dy dx is equal to 1. Okay, from the first principle. Alright, so let's look at something very difficult and see. Like I said, we are dealing with polynomial functions, okay? So take notes. So, like you know, if I have a function f of x equals the square root of x, how do we differentiate this? Okay, from the first principle that we've learned, saying that dy dx is simply equal to the limits as delta x approaches 0 of f of x plus delta x. So wherever you see x, you put x plus delta x there, minus f of x, which is square root of x, over delta x. Okay, so this means that we have a set situation here. So if I try to rationalize the numerator, if you don't understand rationalization of the numerator of a set, I have a video on it. You can search, or you can just open my channel and you would find the video there. Okay, so in the video I said we can actually rationalize both numerator and denominator, so I'm using that idea here. Alright, so if you try to rationalize the numerator, this is how we get. Okay, now this we can limit as delta s approaches 0 of, now we have the same thing here, difference of 2 squares. Sorry, the denominator is supposed to be multiplied by the same thing plus square root of x. Okay, then we get something like this, the first one squared minus the second one squared. So when I have square root of, so let me write it. Okay, I don't want to just quote it there, squared minus square root of x squared. Okay, all over delta x into square root of s plus delta x plus square root of x. Okay, so this is what we have. Now let me erase some parts and it will be very simpler for you to see. Dy dx is actually equal to limits as delta x approaches 0 of, alright, this square will give me s plus delta x minus x all over delta x square root of s plus delta x plus square root of x. Okay, and this will give us let me erase the down one. Alright, so if I have f of x equals, let's say, x squared plus, let's say, 2x plus 1, then if I want to find the derivative of the whole of f of x, dy dx will be equal to differentiating this term alone plus differentiating this term alone plus differentiating this term alone. Okay, but there are some special cases that you should know. Alright, if I have a function like this, if f of x equals some constant c times x, then dy dx will be equal to c times differentiating the whole of f of x. Okay, I'm sorry, let me put it on the right. Okay, alright, so what this means is that if I have a constant multiplying some function, okay, if I have something like d f of g, or let's say f of x, if I'm to differentiate the whole of this, once d is a constant and it does not include any x, then I can factor my d out and find d of f of x dx, meaning just differentiating the side that is containing x alone, and after that multiply by the constant 2. So with this, you just differentiate x, and when we differentiated x from the first principle, we had what? 1. So after that, you can multiply your 2 by 1 and you get what? 2. Okay, then plus differentiating this side. When you do it from the first principle, this side, it will give you 2x. Okay, so it becomes 2x plus 2. Then for 1, if you do it from the first principle, we'll get 0. Okay, so plus 0, and that will be 2x plus 2. Now if you look at this clearly, it's as if we just multiply this power 2 in front and subtracted 1. Okay, so I'm going to write a general formula for find the derivative of a function, a polynomial function. Okay, so if you have functions that are adding, like I said, like this one, okay, there are different polynomial functions, we are adding them, so we differentiate them term wise. Okay, alright, so let's look at it. Sorry. Alright, so in general, if I have f of x equals some x to the power n, then my dy dx, or the differential of f of x with respect to x, is equal to n times x into this. This is very easy, right? So you don't need to be using limits, you don't need to be going through a lot of computations. Just do this and you are done. Okay, so example like we did, okay, we had a situation where f of x equals to what? X. Now we are saying that the power of x here is what? 1. Okay, so what we do is, then our dy dx, mostly represent derivative by dy dx, equals the 1 times x to the power 1 minus 1, and that will give me 1, because times x to the 0, and x to the 0 is 1, so 1 times 1 is what? 1. Alright, the one that we did and had square roots, okay, f of x was equal to what? Square root of x, and when you differentiate this dy dx, this is the same as saying that f of x equals what? X to the power half. I've done said video, so if you don't understand this, you can go and watch my video and you would understand. Okay, so dy dx from here will be equal to just the half, then x to the power what? Half minus 1, that will give me what? Negative half. And from indices, we know that, so I'm writing it down here, dy dx will be equal to 1 over 2. Then since from indices, we can write this as the whole of this 1 over 8 to the power half, and x to the power half is what? Square root of x, so it becomes 2 roots x. If you remember, this is what we had. Okay, so this is the easiest way you can differentiate any polynomial functions. Okay, so this is a basic to differentiation. In our next video, we'll talk about differentiating product of polynomial function, division of polynomial functions, and a whole lot of function of a function, how to differentiate trigonometric function, logarithmic function, and exponential function. So we treat all of these under differentiation. So take this, go through it, digest it, understand everything that you are coming to do, so that next time when we start, you'll be okay with everything that we use. Okay.